quick. Now, here you can see the 3D printed oil cooler allows your oil to pass through, and we've got a set of features on the exterior and the interior that allow us to maximize the rate of heat transfer from our oil. So of course the oil buildup comes from friction, from the pumping of the components through, or the oil through your components, and actually carrying out your work. And so you've got to take that heat that's produced throughout every other portion of your system and then remove it over here in your oil cooling heat exchanger. So, of course, the temperature rise that occurs as the system's operating is undesirable. You can get to the point where the oil will begin to break down or at least degas within your system, and that's on you. So the oil flows through a series of tubes in our heat exchanger, and inside the tubes we have internal features that allow us to perturb the oil flow, keep boundary layers thin, and allow us to remove heat to the walls of the tubes. And then air passes through the heat exchanger like a traditional style radiator, then pull away the heat from our hot tubes. Now, in order to get the maximized heat transfer, we'll have to see some of these internal features here that we'll swing into in just a moment. So moving along into the oil stream, into the heat exchanger, we'll show you some of the fundamentals of the internal features first, the offset strip fins that are used to help the oil flow. You can see them here. As the oil flows through the passages, there are a series of fins that are offset from each other as you go. And that takes your large oil flow boundary layer, which is not good for heat transfer, as heat has to move from the center all the way to the walls of your tubes. And instead, you're able to break up these laminar layers into smaller layers that allow faster heat transfer. So as we advance on, you'll see what it looks like. A traditional tube with no internal offset strip fins tends to have difficulty in actually moving the heat to the edge of the system. Now what we've included are a series of fins that will be introduced next. There they are. And so now, these were printed directly inside the tubes, and the tubes are a shaped tube. And so traditional brazed inserts that would be used to include a feature like this wouldn't be functional with a shaped outer tube. It would be very difficult to actually include. So with 3D printing, we're able to add these features inside our shaped tubes to break up your thick, viscous oil flow to get thinner boundary layers, as well as more surface area inside your tube to help you more rapidly move the heat from the oil to the walls of your tube. So these offset strip fins, again, provide benefits from the surface area and from the fluid dynamics point of view. Now feel free also, if you have any questions about the process as it's going on, to chime in. We'll answer it as we can. The other interesting aspects, aside from the internal features, are the external features of our oil cooler, which once we finish passing through the offset strip fins here visually, we'll show you the air side and what we've done for that. There we go, and exit it. Now here we see the external flow, so the other side of our heat exchange system. So air needs to be drawn through our heat exchanger, and we need to maximize the external surface area. So of course we need some sort of fins to go between our tubes to allow us to get as much heat transfer as we can. Well, at the same time, we also need to be able to print this device. And so these fins, you'll notice, have a slight angle to them, and that's due to the fact that the 3D printing requires that you not have horizontal surfaces that are unsupported in the process. So that's how we end up with these unique shaped fins. Now the tubes themselves are also shaped to help the airflow be maximized. You'll notice that they have a lenticular or aerodynamic shape, and that allows us to reduce the pressure drop. And now we're able to produce those uniquely shaped tubes with those internal offset strip fins because we're using an additive manufacturing process. So in a single printing operation that goes in the tube direction, we're able to crank out a device that's ready to operate with low pressure drop, lower pressure drop than circular tubes will provide, and maximized heat transfer on the oil side. So there we see, with these unique shaped tubes, we maximize airflow and, again, maximize heat transfer, which is our main goal of this system. Alright, so then you can see those features together is sort of the big thing. We're able to include external fins for maximized surface area, external shaped tubes for aerodynamics of the flow to reduce pressure drop, and internal offset strip fins to break up those thick viscous boundary layers that you have with oils in order to get maximum heat transfer. Including all of those different features in a single device is something that's uniquely possible through the 3D printing processes. So additive manufacturing has brought us a great device that is a drop-in replacement, completed in a single printing operation that only requires the hydraulic fittings be added and some mounting points created. So that covers our process. So, if there's any questions about the 3D printed heat exchanger? If not, sure. So the testing. So after we produce this heat exchanger, of course, we need to validate the design. And so we took this heat exchanger along with the stock heat exchanger from the Excavator and brought it down to Adams Thermal, an engineering company that actually produces heat exchangers. And they tested it in a wind tunnel setup, providing oil at the design flow rate, at the maximum oil temperature, to verify that the device can actually sustain operation under those conditions. And we were able to successfully push oil through, no leaks, no problems, and operate at the highest temperature that the oil can enter at, and successfully cool it down and provide performance that would work for the device to be able to operate. So we successfully did produce a drop-in replacement essentially for the stock heat exchanger.